video we're going to talk about electrochemistry. What electrochemistry is it's reactions that involve the transfer of electrons from one substance to another. So if I have here a beaker of copper 2 chloride solution, if I take a piece of zinc metal and I drop it into the copper 2 chloride solution, I can see almost right away, in fact I see the zinc is starting to get dark, almost immediately I see copper metal starts to form on the surface of the zinc. So let's look at the reaction that's occurring. I've got copper 2 chloride and zinc, there's my reactants. My products that are forming, copper is forming and zinc chloride solution. This particular one and a lot of these electrochemical reactions make sense if we break them down and put them in net ionic equation. Copper 2 chloride in solution is this. The copper ions are separate and chloride ions are separate. I have 2 chloride ions per compound, and then let's break the other aqueous solution out. So I'm going to break those up to make the net ionic equation. What is my spectator? Chloride ion's not doing anything here. It's just there keeping a balanced charge. The chloride ions are not part of the reaction. What is my net reaction? I've got copper ions in solution, which have a positive charge. They have lost their 2 electrons, reacting with the neutral zinc metal to form copper metal and zinc ions, which now go into solution. So what I really have is a transfer of electrons from zinc to copper. Electrons are going to go this way. This is an electrochemical, we call it an oxidation reduction reaction. A transfer of electrons from zinc to copper. So zinc was neutral, zinc loses electrons, becomes positively charged, and the copper, which was positively charged, becomes neutral. So zinc loses electrons, and we say it has become oxidized. If something is becoming oxidized, meaning it's losing electrons, something else needs to gain those. Copper 2 plus is my reactant. Copper is gaining. And we call that being reduced. We can think of being reduced meaning it's adding negative charges, gaining negative charges. So this value, this charge is being reduced from less positive to, or from more positive to less positive. It's being reduced. So these types of reactions where I have a transfer of electrons from one to another, they're called oxidation reduction reactions. And as what we'll see, if I've got a transfer of electrons, if I make those electrons go along a wire, I've generated electricity. And so with these kinds of reactions, we can make batteries and such and things like that. Let's look at a couple other reactions. In a previous video, I had dropped some zinc into a solution of hydrochloric acid. Here's an unbalanced equation. Let me balance it. And what we saw is the zinc started to dissolve away. Was it being attacked by the acid, and hydrogen gas bubbles formed. Well, this also is involving a transfer of electrons. It's an oxidation reduction reaction. An active metal being attacked by an acid involves the transfer of electrons. Let's turn this one into a net ionic equation. Hydrochloric acid in solution means I've got hydrogen ions and chloride ions. So it is broken up into ions. That's this acidic solution. Break this one up. Break my aqueous solutions up, take the spectator out. Chloride again is a spectator. And then let's rewrite this one. In this reaction, again, I have zinc getting oxidized, losing electrons. electrons are being transferred from zinc, this time to the hydrogen ions. Hydrogen ions, which were positive, become neutral. Hydrogen as a neutral element is a diatomic, a gas. So I've got 2 electrons being transferred. Each hydrogen takes 1 electron, becomes neutral, bonds together to become H2 gas. And so zinc is oxidized. Meaning it loses electrons, and hydrogen, the hydrogen ion, is reduced. So some reactions involving metals and acids are actually this kind of thing. Electrons are transferring from the metal to the acid. And now one more reaction with the halogens. Okay, if I take chlorine gas, so chlorine in its neutral state, and I'm going to bubble it through a solution of sodium bromide. I have another halogen here that has a negative ion. So let's write that one. I'm going to take chlorine gas, react it with sodium bromide solution. I'm going to get a transfer of electrons here because chlorine actually will pull electrons into it because it's a smaller atom with the same kind of core charge. It will pull the electron from bromide, and I will get bromine becoming the neutral compound. Bromine as liquid, and then we'll get sodium chloride in solution. So that electron that bromine had comes here to chlorine. Let's balance this out. I need to double this and double this. That's my balanced equation. And again, let's turn this net ionic because for these oxidation reduction reactions, the net ionic equation shows much more clearly what's happening. 2Na plus, I got 2 bromides, chlorides. So I take the aqueous solutions, I break them up. Let's get rid of the spectator. Sodium is the spectator, not changed at all in this reaction. And I get chlorine gas. Chlorine was neutral. Bromide had an extra ion. Now bromine is neutral in the end, and chloride. So chlorine, so we have to look at, okay, oxidation is losing electron. Who lost an electron? Which one became oxidized? Bromide lost an electron. So bromide it had an extra electron. It no longer has that. It's now neutral. Bromide loses an electron. Losing an electron, we say that is oxidized. Which one becomes reduced? Chlorine is getting a more negative charge by adding the electron. Chlorine gains an electron. It is reduced. So in these oxidation reduction reactions, a transfer of an electron takes place, and one element has to become oxidized, another is becoming reduced. Okay, let's look back at our beaker again, and I've got now so much copper that's formed on here that the copper is starting to flake away and form these big chunks of copper metal that's starting to flake off. And my solution should be a little less blue than it was, because the blue in the solution was the copper ions. The copper ions are coming out of the solution and adding to the copper metal form. So as this reaction is going and proceeding, the solution becomes less blue because I'm losing copper from solution. I'm forming copper metal, and I should be getting zinc ions, which are clear, and you can't really tell the color from that, going into solution. So let's draw a particle model of this reaction. What's happening in the beaker is the copper ions from solution are coming in here and forming copper metal. Zinc is leaving the metal as it transfers its electrons to copper. It's leaving the metal and it is going into the solution. So the zinc should start to reduce in mass. This amount of zinc solid should reduce in mass because those zinc atoms are going into solution as ions. Copper, I'm going to start to gain copper metal as this comes in. At the particle level, here's my zinc solid, here's my copper in solution. The copper, remember the solution is moving all around, copper comes in here, comes in contact with zinc. Because copper has a greater affinity for electrons than zinc, zinc will hold electrons less strongly than copper. If these two come into collision, copper in a positive state, zinc with all its electrons, those electrons are going to transfer right over to the copper, and I get copper takes the electrons, becomes a metal. This zinc atom goes into solution. So they collide with each other, electrons transfer over, zinc is now an ion, it's in solution, copper metal starts to grow. And it transfers one for one. These reactions are always one atom with one atom. In a lab we had silver ions in solution. Silver is only a single plus. And so what I'm going to need is, I've got zinc is going to need to be in solution, it's going to need to be 2 plus. So I'm going to have 2 silvers come in. Each one takes 1 electron for every 1 zinc that goes into solution. So it's not always a one-for-one transfer. Sometimes I can have different ratios of how these transfers take place, but it's always whichever one. Silver has a greater affinity for electrons. It comes into contact with zinc, which readily releases the electrons. Silver takes the electrons. Zinc becomes the positive ion. Let me take this thing that's occurring in the beaker and let me separate out. So what I have is oxidation occurring. I've got zinc becoming oxidized, losing electrons, copper gaining. I'm going to take this, the fact that electrons are being transferred here, but I want those electrons to transfer over a wire. If I separate this reaction out into the oxidation in one beaker, reduction in another, I can make those electrons transfer over a wire. That'll give me electricity. I can make a battery with this. So what I'll do is, in one beaker, I'm going to put solid zinc in a solution of zinc ions. So I've got zinc in its reduced state, zinc in its oxidized state together, so that I can get them to interact. I'm going to put in the other beaker copper in its positive ion or oxidized state and copper metal in its reduced state, neutral state. And I'm going to put that in another beaker. So I've separated the two out. And then I'm going to attach a wire to them. So I need them to be able to exchange ions. I'm going to put a little voltmeter here so I can measure voltage. I'm going to put a wire there so that electrons can transfer. And I say, okay, well, which one is giving electrons to who? Copper wants the electrons more than zinc. So electrons would start to transfer here along the wire to the copper. But I have one problem. As soon as I start sending electrons over here, this beaker is going to start to build a negative charge. And so as soon as electrons start, they're not going to go very far because I'm going to start to build a negative charge. So I need to do something to balance the charge. I can't put a negative charge here. So what we do is we put a little bridge across filled with any kind of salt solution. I'm going to put a salt solution in the bridge. In here, just some kind of tubing with some kind of filter in there that I can put a salt in. Now I've got some charged particles that can balance this charge. Negative charges come along, electrons come in here, add here, and so what I can do to balance that, I'm going to send positive ions, these positives, are going to start to come in here. I'm adding negative charges. I'm going to balance the charge. So what that's going to have is these ions, the positive ions from the salt, are going to come in this way. The negative ions are going to transfer in here. Because I'm losing negative charge, I'm going to start to put that negative charge back through the salt bridge. What I have is a continuous circuit with electrons flowing throughout, and I have a battery. This will generate a voltage. I can start to power some kind of electric circuit with this. So let's look at what's going to happen as this battery starts to work. Electrons start to transfer on here. So when the zinc loses an electron, it goes into solution. I'm getting zinc going into solution, becoming positive zinc ions. Plus, well, this is of course not balanced. I need to balance the charge. What's happening in this case? I am releasing 2 electrons. So this is what's happening in this beaker. Zinc gives away electrons. The zinc comes here. The electrons go up the wire. What's going on in this beaker? I've got copper ions adding to the metal. Copper ions. So these electrons transfer through here, through the metal. A copper ion comes in contact, takes those electrons, and I get solid copper. So the electrons transfer here. I'm taking copper from this solution, putting it on here. This electrode, this piece of copper metal, is going to start to grow. It's going to gain mass. This zinc electrode, I've got the zinc is going into solution. The metal zinc is going into solution. This one's going to start to shrink. And so I've built a battery that's generating a voltage. So why do batteries start to die out over time? After a while, I'm getting too much zinc in solution. This is getting a high concentration. I'm losing this. This is getting a lower concentration. And the battery voltage starts to drop. Let's label a couple more things on our battery. What we call this one, here's the reaction where zinc is getting oxidized. This is called the oxidation half reaction. So in this cell, I've got oxidation going on. We call it a half reaction because I can't have oxidation without these electrons going somewhere. If something's getting oxidized, something else has to be reduced. The other half of the reaction is in this cell. This is called the reduction. The reduction half reaction. So oxidation here, this is the half reaction for reduction. This is the half for oxidation, for reduction here. I can, of course, combine them back into one equation if I add them up. Let me take the 2 half reactions, oxidation and reduction, add them together to get the full reaction. I'm going to add up all of my reactants over here, all of my products. If I can see that I've got electrons and electrons, they're going to cancel out. So what is my reaction? Zinc and I have the overall reaction that occurred in the beaker by itself. Zinc giving away electrons to copper, which becomes the metal. There's my complete one. Okay, let's look at another type of battery chemistry that we can build, or electrochemical cell. I'm going to take a piece of magnesium and put it in a solution of chromium-3 nitrate, and I'm also going to take a piece of chromium and put it in a solution of magnesium nitrate. Now in these beakers, I didn't bother showing the nitrate because the nitrate's just there. It's not really part of the reaction. And I'm going to do these things because I want to say, well, I don't know which one of these 2 metals attracts electrons more, which one would get oxidized more readily and which one reduce more readily. So I'm going to build these 2, and I'm just going to observe. one of them will have a reaction, one is not going to have a reaction. So if I put magnesium with all its electrons and chromium in a positive state, what I'll see in this one is I will see a reaction occur. I will see chromium metal start to grow here, so that means that chromium will go into solution, and I'm going to see magnesium ions come out. If I put this combination into a beaker, magnesium in its neutral state, chromium as a positive ion, I see a reaction occur. I say, well, I'm going to try that. What if I put chromium in its neutral state, magnesium positive? Will a reaction occur? And let's look at that. So if magnesium readily releases electrons, more so than chromium, if magnesium were to come in here and grab electrons to form the metal, but then I've got this same situation, so what's going to happen right away is it's going to immediately give those electrons back. So because magnesium more readily releases electrons, it's not going to take the electrons from chromium. In here, no reaction. I get no reaction here because the magnesium is more easily oxidized. It releases electrons easier. So from trying this combination, I've determined that magnesium is the one that's going to be oxidized more easily, chromium not so much. And so I can build my battery with this. So let's use this chemical reaction to build a battery. Here's the reaction that's going to occur in the battery, the overall reaction. Solid magnesium is going to give electrons to chromium. Magnesium goes into solution. Chromium forms the metal. What I'm going to get, though, this is not quite balanced. I have my atoms are balanced, but notice the charge has to be balanced. I'm transferring electrons here. I've got a 3+ charge here, 2+ here. I've somehow have gained an electron out of somewhere, and I can't just gain electrons from nowhere. So I've got to balance my charges. I see a neutral, a double even number here. I'm going to double chromium. That gives me 2 3+. That's a total of 6+. I need 6+ over here. I'm going to triple magnesium. So when I'm balancing these things in their net ionic form, I need to make sure my charges are balanced. I can't lose or gain electrons. So I've got 6+, 6-, that's perfect, it's balanced. Now make sure all my atoms are balanced. Magnesium, I have 3, I need 3 here. 2 chromiums, I need 2 here. Here's my balanced net ionic equation for this reaction. Now let's build our battery. So here's my battery. Sometimes when we see a problem like this, we'll say, okay, which way will electrons flow? So I want to draw the electrons. Which way are electrons going to go in this wire? Well, I can see from my reaction, magnesium is the one that's going to give up the electrons. Electrons go this way. So far in both the batteries I've shown electrons coming from left to right. It's not always that way. But it's just which one is more easily easily oxidized. That one gives up electrons. Electrons come around here, go into chromium. So chromium is gaining electrons. Chromium ions come in. This electrode grows. This one starts to shrink. Magnesium ions are leaving the electrode, going into solution. My oxidation half reaction. My reduction, so chromium is being reduced, it's adding electrons. Here's my reduction half reaction. I don't have to balance these. I can see 2 electrons transferring here, 3 being gained. Of course, we can balance them when we combine these into one, we balance them out. But I can write the half reactions like this. Now, as I noticed, so let's look at the salt bridge a little bit more carefully because we've got to label these electrodes. I've got negative charge leaving. I need to bring some negative ions in here. They're going to go this way. In this little bridge, I'm going to have a flow of negative ions going this way. I've got negative charge building up here, so I've got to bring some positive to neutralize that. That's going to be the direction of flow of ions in my salt bridge. And that also is how we label these electrodes. So if positive ions are called cations, negative ions are called anions. So I'm going to label these anode and cathode for the electrodes. Anions, negative ions, go towards the anode. Negative ions are coming in here. This one is called the anode. The cations, the positive ions, are coming this way. This one is for the cathode. So in the cell where reduction is happening, that is the cathode. Cathode reduction happens at the cathode. Oxidation happens at the anode. And the easiest way to remember is what's going on in my salt bridge. Oh, positive ions are going this way, cations are going this way. That's the cathode.